anything related to this course? Nothing. What did I get this one? All right, y'all, I mean, homework was up there, y'all get it done, everything?
I'm just looking real quick to see.
Second part was a lot harder than the first.
Which one?
Just your problems compared to like the book problems.
All right, which one you want to do?
Uh,
I always try to do one problem related to fire.
Do number one, it's magnetic field strength of H equals, at the value H is 5 mu.
Hold on one second. This is brand new markers, can I tell you one thing about them? Or they're out of the box, but they've probably been in the box for 2 years at least since COVID. Another bad one. Okay, nothing but deads. Fine. Go ahead.
Okay, magnetic field strength of 5 milliamps per meter is required at the point theta equals 90 degrees, R equals 2 kilometers from an antenna in air, reflecting ohmic losses, how much power?
R equals 2 kilometers. Go ahead.
Reflecting ohmic losses, how much power does the antenna transmit if it is a short dipole length, L equals lambda over 25.
Short dipole. Right, now this is really gonna level with you. When you're dealing with this kind of stuff, what I always think of, the minute you see short dipole, think of 3 things really. First, for short dipole, the average power density will always be the total radiated power over 4 pi r squared. That's just the isotropic power. Then multiply it by the gain, or really the directivity. And that is simply going to be 1.5 times the sine squared of the angle. And that's in the AR direction. That's the first thing I always put down. Second thing is, you know that the radiation resistance is going to be 80 pi squared L over lambda squared ohms. Right? So that's the radiation resistance. This is how I do this problem. Third thing is finally the E field. I know the E field for a short dipole is J eta beta I times the length L over 4 pi r times e to the minus j beta r times the sine of the angle theta and the A theta direction. And again, the E field is, we're assuming the dipoles align on the z-axis. Theta is measured from the z-axis to the r radius vector. And these are just the standard equations. Do y'all agree with me here? Now he gives us something. He says we're 2 kilometers away, we're at 90 degrees, and he gives us the H field. He doesn't give us the E field. So we have the H field out here of 5 amps per meter squared, or 5 milliamps per meter, pardon. All right, if I have that, I just multiply by 8, and now I have the E field. Do y'all agree with that, class? I'm going to work this a couple different ways. Now, they give us also the length of the short dipole is lambda over 25, is that right?
Yes.
All right, and what do they want, the current?
How much power does the antenna transmit?
We can get that in a second. Do they want the current or not?
No, they don't this point.
All right, well, at this point, we can do it. There's several ways to do this. I'm going to do it a couple different ways. I start with the H field here. All right. I know that the average power density, PF, right here, right, would be equal to 1/2 magnitude of E squared over eta. Y'all agree with that, first of all? Everybody with me? That's also equal to 1/2 times eta times magnitude of H squared. Y'all agree with that? That would be watts per meter squared. Do you follow me? Because I just replaced E with eta. E with eta times H. Then you get the second one. And this is in the AR direction. Right. Now, I have the H field. I can get the average power density, correct? Everybody follow me on this? I'm just going to say that I know this will be 1/2 times 125, you don't need to calculate this, times H, and H is 5 times 10 to the minus third squared. I'm gonna just leave it like that. I'm not gonna mess with it right now. I know that's the average power density. Here's the average power density. Y'all follow me on that? All right. I wanna make sure everybody sees this. There's so many ways to do this problem, and you can't go wrong. All right, now I look here, and I'm gonna modify this. The angle is 90 degrees, right? Go ahead.
So does this mean that there's no P normalized?
You don't need it for this one. I've given you the three equations that we've already got the gain here, right? The normalized power is gonna be just sine squared theta for a short dipole, always. That is the normalized power. All right, now follow me on this one. Theta is 90, correct, by the problem statement, right? So, what is the sine of 90? 1, right? Sine of 90 is 1. Just think about it. 90 degrees, it's 1, isn't it, class? Some of these you kind of have to know by heart. So, I'm just going to say this, therefore, has got to be equal to this, which is 1/2, and it's going to be times 125 times 5 times 10 to the minus third squared. Now, I'm doing it this way for a reason. I'm going to show you, I'm going to get P rad directly from here. You all with me? I can get it a different way. All right, now, y'all see that R is 2 kilometers, so I have one equation with one unknown, don't I, class? You're writing it down, scribing, but this is not so mysterious. Once you have those 3 equations in your head, and you work with them, you can't really miss E field. We'll give you the H field. The gain that I have, or the directivity, will give me the average power density based on total power radiated. Depending on what I need, I can get anything. All right, now I need P rad, right? So I'm gonna divide this by 3/2 for starters. That's getting rid of the 1.5. And then I multiply it by 4 pi r squared, and I get P rad. So then I multiply this by 4 pi. R is 2 kilometers, and 2 times 10 to the third squared. Y'all agree with that? We can play games and cancel things. Let's see here. The 2 and the 2 here cancel, don't they? So get rid of that. Then I got 3 into 120 pi. That's 40 pi, right? I'm just trying to cut down on my work I need to do. 40 pi, let's see. Well, at this point, we can keep going, but if anybody's got a calculator, can you just brute force that and tell me what the answer is? I mean, I can keep canceling. I got 10 to the minus 6 there, 25. Then I got 10 to the 6, so those cancel, so I'm gonna have 25 times 4 times 4 times 5 times 5 times 40. And if you can give that to me, I'd appreciate it. But again, I'm just using the simple equations, getting it straight. We're gonna do it a different way. Everybody okay with that? And by the way, you are recording, right? Thank God. I hope this helps, getting a video record. I mean, I've heard a lot of students thank me for doing that, but I don't know why everybody doesn't do it, because, I mean, you're paying for the course, you know, God forbid you're sick, you can at least go back, watch the entire lecture. If I make mistakes, you can correct me. I'll announce it. Yeah.
It's 0.1579 watts, and the
1579 watts. Go ahead.
yeah, the H field is microamps.
Oh, it's micro. Wow. Micro is 10 to the minus 6. My bad. So that means over here, I need to put 10 to the minus 6. My bad. And you took that into account?
Yes.
Okay. Is that the answer? The right answer? Is that the answer in the solutions? Okay. You all follow me on that? That's getting it using gain or directivity, and that's the way I usually do this if I'm looking for total power rating. Now, we don't have to do it that way. If we have the H field, not milliamps, but microamps. Now, follow me. If I have that, here's what I'm thinking. I have this equation for the E field, right? I multiply the H field by eta, and I have the E field. You all agree with me? Now, theta is still 90 degrees. You all see I can go ahead because I know L. I can get I naught directly from here. Do you all follow me on that, class? I'm gonna just do this one time so you can see everything. So I'm gonna take this, and the only thing we care about is the magnitude of the E field at this point. That's equal to eta times the H field. All right, I'm just gonna leave it as the H field here. Now, if you just follow me on this, remember, it's just magnitude I'm worried about. Y'all follow me? The reason, because the H field will give me the magnitude of the E field. The magnitude of the E field will give me the current. Y'all with me? Okay. So now, since it's magnitude, I get rid of this J and I get rid of this, right? All right, next thing I'm gonna get rid of is that symbol because we don't care about the vector direction, we're caring about magnitudes. Sine of theta is 1 because theta is 90 degrees, get rid of that. Now, when I take a look at this, eta appears on both sides, so I get rid of eta. After that, I can see that I naught, and I'll write it here, I naught will become simply, if you look at this, I have my H field, right, that I'll put in times 4 pi r, right? And then I divide it by beta L. Well, beta, I'll go ahead and use beta times L. Now put in the values. H itself is 5 times 10 to the minus 6, right? Then I have times 4 pi times r, which is 2,000. Then I divide by beta, and beta is 2 pi over lambda times length, and length is lambda over 25. I'm gonna stop and just let you see. The only thing I've done there is replace the unknown, the symbolic values with the actual values. Everybody okay with that? Take a good look, make sure you're okay. Now, when I do that, I'm over here. Y'all see how lambda cancels? Right? So I'm going to get rid of lambda. Let's see. I'll try to simplify. I always do this when I'm doing this. I've got 4 pi and 2 pi. That's just 2 on top, right? I'll leave it as 2. And then I have 25, 125 downstairs. I'll take it upstairs as 25.
I think it was 2 over 25.
Pardon?
I think you had 2 over 25. Or was it 1?
Beta is 2 pi over lambda. L is what?
Oh, I see. Oh, you can't. I'm sorry.
All right, now if you get back to here, can somebody just do the math? I mean, what is this going to be? It's going to be what? 50 times 2 is 100 times 10 to the third times 10 to the minus 6 times 5. What do you get? What's that?
1.5 amps.
0.5 amps. Anybody confirm that? Just be sure. Okay. We get that. Now I'm going to go and I'm going to get the radiation resistance. I've got the current. The radiation resistance for this is what? 80 pi squared times L, which is lambda over 25 divided by lambda. So it's really 1 over 25 squared. Y'all agree with that? I want to make sure I do all aspects of this problem. I get the radiation resistance, power radiated, every average power density. And can somebody tell me what that is? That's a small number. 625 and 8 pi squared. I can't do that in my head.
1.263.
Anybody confirm that? 1.263 ohms? All right, now, if we have the radiation resistance and the current, remember that current we're getting is a P current, right? It's not the RMS current. So now we can find P rad for this one as simply 1/2, and then it's going to be times I naught squared times R rad, which is 1/2 I naught squared, that's 1/2 squared, times R rad, which is 1.263, right? And what do you get for that?
0.157.
All right, 1.1579 up there, but 0.1579. They agree. Now I've done the thing. I've done it using just the radiation resistance, using the equation for power radiated because I knew the gain, it's a short dipole, right, or directivity. Or I got the H field, then the E field, then I got the current, then I got the radiation resistance, then I got it. So I've done it either way, you'll always get the right answers. And there isn't just one way to solve these problems. There's probably the path, they're the same thing you're doing, but you can go through it many, many different ways and get the same answer, okay? Any questions about that? That's a good problem. There was one problem, it was I think the last one I put up there, you said it was harder. You know, I put some problems up, did you do that?
And then coils.
Oh, the coil ones, I gave you those problems, but the only thing you had to do is include the number of coils and the turns, the number of turns, but I gave you that. The radiation resistance changed, that's the deal. I don't really.
That actually, it was the problem we were doing, because the second part of it is where you do the 10-turn loop.
All right.
antenna, So,
Well, so for a short dipole, that's the whole thing. If we're gonna do a coil, then they want what? The power radiator current or what?
the same, yeah, the power radiated.
The power radiator will be the same, and I wanna tell you one thing. For both the small loop antenna and the short dipole, the gain is the same. Do you all follow me on that? Directivity and gain are the same. You understand that? The only thing that changes that's different is the radiation resistance, okay? Now, when you think about that, since the gain is the same, the power radiated would be the same. And I'll tell you why. Remember, it doesn't matter how many loops there are. The power radiated, we know that PAV, the average power density at any range, is going to be the isotropic power radiated, right, over 4 pi r squared. So that's the isotropic power radiated, is the gain. Loop antennas, I mean short dipoles or small loops have the same exact gain. It's 1.5 times sine squared. So this is going to be times 3 halves times sine squared theta. And we know that the average power density of the H field is the same. Over here would be 1/2 magnitude of the H field squared times eta. Now, this is gonna be the same for both of them. That means and this is gonna be the same for the loops, right? That means the total power radiated will be the same. Does everybody give me that? Do you agree with that? Because it has to be, because the gain's the same, right? The directivity for both of them is 1.5 sine squared of theta for small loops, right? And for short dipoles. That means the total power radiated is the same. However, the difference is the current and radiation resistance will be different for the loop compared to the short dipole. Here, the total power radiated, which will be the same, will be equal to 1/2 times I naught squared R rad. That means for the short dipole or for the multi-loop antenna, this product will be the same. Y'all follow me on that? However, there could be more current or less current depending on the number of terms. And then there would be an associated higher or lower radiation resistance for the loops. Do y'all follow me on that, class? What does it ask for that loop antenna? Where did I ask? I don't remember. Did I ask for the current? I don't know. Did y'all do them? Out of curiosity, how many did that one? You just be honest with me. When you did it, did they ask for the current or just total power radiated?
Just power radiated.
Then that's the same for both. It's gotta be. All right, and you probably found that out the hard way if you ran through and got the current. But that's the eureka moment where, oh, I didn't have to do that. All right. Anything else? All right, I'm gonna give you one. Before I go on with my lecture. And just think about what I'm doing. I'm gonna say that I have an E field. The E field itself is gonna be, this is a fictitious E field, as 20 over R, right, times cosine of theta, e to the minus j beta R, okay? Just giving it, that's it, that's the E field. Who knows what creates it? We don't know if it's feasible or not. And I want a few things. I want the directivity maximum for this antenna. Some antennas creating it, so I want that, right? I want the total power radiated. How would you do that? By the way, this is a typical kind of quiz test problem. So how would you do it? Actually, I gave you a problem similar to this.
You have to find H field.
Well, you don't really need the H, that's total power radiated, right? Right? I'm asking for the wattage radiated. Now look, from the E field right here, just listen to me, all right? Can we get the actual power, the radiated power in the far field? Yeah, we could, and this may be what you're going at. We could say the average power radiated, technically it's 1/2 the real part of what? E cross H conjugate, we have to get the H with one for this. But we know from the far field, it's 1/2, right? Magnitude of the E field squared divided by eta in the AR direction. Y'all with me, class? That's it, right? Now, if that's the case, I come down here and I say the average power density radiated is going to be 1/2, take the E field and square it. Now I get times 20 over R, right? Forget this, squared times cosine squared of theta. Y'all with me on that, class? Right, I've got to divide it by eta as well, right? I've got to take this and divide it by eta. But, and this would be in the AR direction, and that would be the total, that's power density, right? Now please watch this. If we wanted to get the directivity max for this, we'd start by getting the normal, P normalized, the normalized power density. When you take one look at that, what does it have to be?
Cosine squared.
Just cosine squared. Y'all hear me around there? So it'd be cosine squared. Okay. Now, if we wanted to get D max, we take 4 pi, and then we integrate, it'd be a double integral, the normalized power density, which is cosine squared of theta, times the sine of theta, times the theta d phi. Here, theta would go from 0 to pi, and phi would go from 0 to 2 pi. You all understand, I'm just taking the formula, and I'm plugging in the normalized power density, correct, class? If you're uncertain about that, D max is actually equal to 4 pi over the integral of the normalized power density as a function of angle times sine of theta d phi. That's what I'm doing. Now, the nice thing about this integral is you don't have to break up a sine cubed. If you take a look, we already have, if you take a look at this, if u is equal to cosine squared of theta, then du, or I'm sorry, make u equal to cosine of theta, make it this one, cosine of theta, then du is simply going to be minus the sine of theta, d theta, right? I'm just going through the motions. You with me, class? All right, now, if that's the case, what happens? Then I get D max, right? Would be equal to 4 pi. And just listen to me on this next part. I'm trying to let you catch up. I know I can move a little too fast, so I'm trying to. Is everybody with me on this one? Almost on. I'll tell you something. All right, when I do the d phi integral from 0 to 2 pi, what do I have to get? Just 2 pi, right. Now I'm left with this integral, and I have cosine is u, so I have u squared, and then du is sine theta, or du would be equal to minus sine theta d theta, so I have minus du. Or now I can just put in minus du here. Then, if when theta here is equal to 0, the cosine of 0 is 1. And when theta is equal to pi, what's the cosine of pi? Minus 1, right? Exactly. Now I have this integration, correct? I'm just putting it down. Y'all see here, to get rid of that minus sign right there, I just flip the limits. Y'all with me, class? Flip the limits. And that's going to be what? 4 pi, I got 4 pi, I'll write it down. 4 pi, then I'm divided by 2 pi, right? And then when I do this integration, I get u cubed over 3. So I get u cubed over 3, evaluated from minus 1 to 1. And that's going to be 2 times that. So now I get 4 pi over 2 pi, or I have 2. Then I have this divided by 1/3, right? And then I have 1 cubed, which is 1, minus 1 cubed, which is plus 1. So I have times 2, and the answer is 3. Eureka. With me? Now again, I executed the integral. If some of your calculators can do symbolic integration, or they can, this is actually a hard integration, it has hard limits, so you can do that in your calculators, but that's different from a short dipole, right?
That's what I was about to ask. So if like on a quiz or a test, if we just put the definite integral in a calculator, would you accept that, or do we need to show you us doing the integration?
Yeah, I mean, well, here's the deal. What you should be able to do at this point is some manipulation. You can give me the final answer, just plug it into your calculator if you do. But I have to see something like that as evidence
Yeah.
that you just didn't copy.
Yeah.
I need some.
At least like the first part of the integral, like we know what we're integrating and just.
Yeah, and one other thing too, now that I have B max and I have the normal power, P normal, the actual value of D for any angle would be equal to D max, right? Times P normalized of theta. So that would be equal to 3 times cosine squared, right, of theta. Y'all follow me? That would be the directivity, correct, class? Okay. Now, next part, how to get the total power radiated? Well, you all agree that that's the power, right? How would I get total power radiated? I bet you see it now.
It's
1/2, 2.
I'm going to go and do it right here.
first you need to find under the.
All right, follow me on this, guys. To get total power radiated, technically speaking, we take the power density at a given range R, right? So we take this, where we would take P average, right? I'll write it down this way. P average, and then we multiply it by what? R squared times sine of theta, d theta d phi, because this is what? That's the differential surface area, it'll be in the AP direction, by the way. I mean AR direction. That's the differential surface on a sphere of radius R. Do y'all remember that? If you don't, just think about this. The differential surface has to have R times d theta, that would be the wiper arm, a range R, wiping it vertically, you might say, with a wiggle in theta, and then it would be R sine theta, that would be the projection of this in the horizontal XY plane, times d phi. So it would be an R squared sine theta, d theta d phi. I'm going to get rid of this because the dot product is going to be this times this is going to be actually equal to 1. And the limits would be from 0 to pi, 0 to 2 pi. You're about to see something that will make your life a little easier. So then I can say the total radiated power would be equal to this integral from 0 to 2 pi, from 0 to pi. Now I took the power there, but I'm going to tell you that R squared and this R squared is going to cancel. So I'm not even going to bother with that. So I have 1/2 times 20 squared. The R squareds are going to cancel. Then I have cosine squared of theta divided by eta, right? And then I have times sine of theta times d theta d phi. Now can everybody follow me? I just wrote down, and I got rid of the R squareds because they're going to cancel, right? Everybody with me on this? Follow me on this last step. I'm going to take all the constants out in front. So I got 1/2, right? And I have 20 squared, and I'm divided by eta, and then I have this. I have an integral from 0 to 2 pi, and an integral from 0 to pi, right, of cosine squared theta times sine of theta d phi. Now does this ring bells? Didn't we just do that? All right, what is that? Well, technically, this right here in Dr. Whitmore's book will have the symbol omega. It's called a solid angle. And it's what we use to get D max. We say that if we have 4 pi over the solid angle, right? There's the P there. This is propagation. We get that. We just calculated that, didn't we? What did we find out it was? It was 2 pi times
4 pi over 3.
well, no, I mean, we got 3, right, for the value
Yeah.
of 4 pi over that. But what was that, actually?
4 pi
I
over
have it
3.
over here. Uh,
4
It's
pi.
gonna be 2 pi times what? Yeah, you're at 4 pi over 3. Do you remember that, class? All right, so this actually is 4 pi over 3, which means the total power radiated is then 1/2 times, you can do the integration if you want, 20 squared over 8. 8 is 120 pi. I want you to do this. And this is gonna be 4 pi over 3. Can somebody just tell me what that is? And that would be in watts. Pi's canceled, that's gone. 4 and 1. 60 times 390. 100 over 90. No, I'm just, don't worry, it's 20 squared is 400.
2.222.
Anybody else? I wanna make sure, 2.222, sounds right, but I don't know.
Yeah.
That's watts. All right, now that problem right there, I think I gave you a problem very similar to that, right? But it makes you think. It gets you into the right frame of mind to think through everything, the relationship between, directivity, total radiated power, normalized power, D max, all that stuff. Okay, now I'll move on with the rest of my lecture. I mean, are there any questions before I go? This is a good problem.
For P rad, would it be wrong to say R squared P max omega P?
Well, that's in Whitmore's book. All right. If you have total power radiated, the way I always do this, I try not to memorize any formulas I don't need. Total power, if I want the average power density, I always go for this. Take total power radiated that you just got, right? Divided by 4 pi r squared. That's the isotropic power density. Now when you multiply it by the gain, really the directivity and gain are interchangeable here, or by the directivity, what it does is gives you how much it's sharpened, the focusing power of the antenna. And then you would just put down the directivity in this case as a function of theta. You choose a theta and I got it. All right. Now I do it this way, because this formula, I've got it down. I mean, I've done this so often. If I got the directivity as a function of angle, and assuming directivity and gain are the same thing, then I find total power radiated over 4 pi r squared and multiply it by the directivity. That is the power density. And if I want E or H, I get this first, then I set the power density equal to 1/2 E squared over eta, and I get E or H, depending on what I want. Follow me, everyone? And that's the way I do these things now. Okay. Now what I'm gonna do is this. I'm gonna show you an arbitrarily long antenna. How you go about getting straight wire antenna centered at the origin, and it's a gap fed thing where it's differentially fed right in the center, and it's gonna be oriented in the Z direction. We're gonna go ahead and get the actual electric field for it. If I was to tell you one thing, I'd tell you at this point, just put your pencils or pens down and listen. I'll tell you what to write down, but I need you to be attentive to what I'm up to. I'll tell you what to write down in a second. So, for this one, now we got an antenna that's longer. It's of the order of lambda. So we got an antenna like this. And it's got a total length of L. Yeah, I'll use small L there. This base is gonna be a minus L over 2. This here is gonna be a L over 2. This is the Z direction. We're gonna say that the antenna itself is from here down to here. And it has some current I, it's a function of z, this is the origin, by the way. And I of z, you don't need to write this down, just listen. You'll be happy to listen. I of z, I gave you last time, is some I naught, right? And then it's gonna be times the sine of beta, and then it's times L over 2 minus magnitude of z. In Dr. Whitworth's book, he does not put magnitude of z. And that is the actual way the current is shaped, the magnitude of the current. So it does something like this. You know? We don't know exactly how deep that dip is, but it's like that. With me, everyone? Now, the way you go about getting the total E field from this, I come up here at a given height z, and I assume I'm going to take a little differential chunk of this current. It's going to be at a height z, and then it's going to have a, boy, I hope I don't mess this thing too bad. It's going to have a height dz, and I'm going to say I'm at that 2 rays. This is the radius vector r. This is r prime, and a long way away from here, I can say that the differential electric field, VE from that, would be equal to, you don't need to write this yet. I'll tell you what to write, just follow. Y'all with me on this? I want to find the differential field from this little chunk of current. Well, that would be equal to J eta beta. Now we treat it like a very short dipole, like a Hertzian dipole. Then it's going to be times I of z, that's the actual value of the current at this point. Then it's times dz. Now that again is the, you know, how thick, or how the height of that, the length of that differential antenna. Divide that by 4 pi. Here, I make the claim that because we're a long way away, we're in a far field, r and r prime are about the same in magnitude. You all with me on that? So if I take 1 over r prime, like 1 over a mile, and compare it to 1 over a mile plus an inch, they're about the same, right? This is a magnitude. So I can just put magnitude of r here, or r. Now, I need to put the sine of the angle, and again, for differential, that's theta, therefore the sine of the angle for r prime or r, if these two things are parallel and I'm a long way off from there, they coalesce at a point a long way away, it's the same for either one, either for r prime or r. And then this is the different thing. Now it's going to be e to the minus j beta, and it would be r prime. What is r prime? We did this last time. Well, it's r, but look, there's a distance difference. Remember, I tried to make a bigger triangle to show you like this. If you take a look at this, right? This distance here would be, the height is z, that's the hypotenuse. This would be z times the cosine of theta, where this would be theta. Can you all see that right there? The projection of z, that's the hypotenuse, onto this, because this would be a right triangle, would be z cosine of theta. It means this is minus magnitude of z times cosine of theta. Can you all follow me on that, class? Now, if you have that, I'll put that in here. This is now going to be r minus magnitude of z, really just z, z cosine of theta. Now I break it up, and I'm going to tell you, this is the way it's always done. I'm going to break it up. I'm going to say that dE, the differential electric field, is now J eta beta over 4 pi r. All right. And then I leave the sine theta here. Now I have to put in the actual I naught times the sine of beta times L minus magnitude of z, or L over 2, pardon me, minus magnitude of z. Put that in there, I put, and I take out the e to the minus j beta r, I take out in front. And I leave e to the minus, or e to the plus j beta times z cosine theta. Right there. And just understand, I've rearranged these terms. I broke this out. So if I had e to the minus j beta times r, I took that out in front. And then I have e to the minus j beta times minus, which is plus z cosine beta, that's there. Now that's the differential electric field. To get the total electric field, you're gonna write the answer to this down. This one you have. When I take the total electric field, I integrate from minus, and it would be L over 2 to L over 2. Follow me? That would give me the total electric field. Well, what I'm really gonna integrate is right here. Now I'm gonna integrate from z equals minus L over 2 to z equals L over 2. And this is the only thing that's functions of z. All this is not. That's a constant. Y'all with me? Now, if you look at this integration, can y'all see what I'm talking about this one? How would you guys do it? I mean, if you had to. If a gun was to your head, do it or die. Boy, I hope I don't get in trouble for it. Well, the way I always do these, and we don't have to do it, but I take this and I use Euler's identity. I take the sign and I turn it into e to the j argument of that sign, minus e to the j, or minus j argument of that, over 2j. Now, once I do that, you can all see I'm going to get a bunch of crazy exponentials. Then I go ahead and I look for a UDU type integration on that, and you will get one, but it takes time. Whitmer's book in the back, he does this, he shows it. It really doesn't help give us understanding to beat this integral down. Some professors, when I have, I can tell you right now, some do it this way. They take the sign, it looks like a sign of A minus B, doesn't it? If you look through, you got two terms in here, separate. So they go ahead and expand it. Then after that, they would take that and turn it to exponentials and beat the thing to death. All right? I don't prefer to do that. I'm going to give you the answer. Because it's not a standard integration that you just, take one look at it. No. The E field, after all this said and done, put this down, write this one down. This is important. That's going to be equal to J60 over R, e to the minus j beta R. And actually, let me put the I in front of it. Now, this I naught is going to be the current at the base of the antenna. I'll mention this in a second. Then it's going to be times e to the minus j beta R. Please write this down. And then it's going to be times something that I'm going to call small f of theta. F of theta itself will be equal to cosine of beta L over 2 times cosine of theta minus the cosine of beta L over 2 over the sine of theta. The reason I know that is I work with this stuff all the time. I don't expect you to memorize this. All right? You learn by use. It'll become part of you after a period of time. Now, that is going to be the E field, and it's in the A theta direction. This is in your book, and I want to give you a point where it's at. So in your book, if you look at all right, he gives you H, it's on page 450. I prefer always giving E. He gives you H, if you take H and multiply it by eta, which is 125, you get this. Anybody got your books here? All right. I mean, if you can see it, I'm just telling you, it's equation 8.71, but you have to multiply by eta. He doesn't give you the E field straight away. I wish he would, because this is the common form. Now, I didn't put the f of theta there. I want you to just listen to me on this next part. This is important. So this is the E field for any arbitrarily straight wire antenna centered at the origin. I got to make one important point. Get rid of this messy thing. Because I want you to see this. You see that I naught there? This is important. That I naught is the actual current at the base of the antenna. Y'all hear me? So that's important. That I naught is the current feeding that antenna right there. Now, if that's the E field, and I want the power density, how do you think I might get it? You guys know me. I'm not gonna look it up on Google, I'll tell you.
Magnitude?
1/2 magnitude of the E field squared divided by eta. I always do that for any propagating wave. That's the way if you got the E field, that's how I do density. So please write this down. So the power density, this is the average power density for an arbitrarily long antenna, straight wire antenna, is 1/2 magnitude of E field squared divided by eta. I want you to take a look at this for a second. All right, I'm going to put the 1/2 down. Now, what is eta? 120 pi, isn't it, class, for free space? With me? Now, I'm going to go ahead and square the E field by looking at it. Just take a look at this. I'm going to square the E field. You see how I get 60 squared? All right? So I'm going to put just 60 squared right here. All right? Then I have I naught squared. By the way, power density will always be proportional to some I squared. All right, power density. I forget about that, and then after that, I have to square this angle. So now I'm going to have the cosine of beta L over 2 cosine of theta minus cosine of beta L over 2 over the sine theta. I'm going to take this whole thing and square it. In Whitmore's book, he calls this capital F of theta. I much prefer using this, small f of theta is my f of theta, because it works better this way. It's better to understand how the E field itself maps out, and then use that square to get the power density. Follow me, class? In his book, he does not. If you look at his book, he's got this information, but he uses a capital F of theta for the squared angle. Now, when you look at this, work with me on this. All right. What is this going to be? I got 60 squared over 120 and divide by 2. So really I got what? 60 squared is 6 squared times 10 squared over 2 times 120 pi. Well, 120 is going to be 60 times 2, right? And then I got a pi. And then I have pi naught squared. I'm just looking at all this junk in front. Y'all follow me, class? Yeah.
Is your R squared supposed to?
Yeah, you're right. Absolutely. There's supposed to be an R squared here. I dropped that ball on that one. My bad. Should be an R squared. My bad. Has to be a function of 1 over R squared. Thank you. Thank you very much. All right. Now follow me on this. Well, I'm trying to just get this down to one value. And you see, if I look at this, right here, I've got 6, well, I can do this. I can make that 6 and this 20, right? So I have 6 squared over 6, that's simply 6, right? So I have 6 divided by 2, and then I have times 100 divided by 20 divided by pi. So I have 3, so that's 15, right? 15 over pi, I naught squared over R squared. And I think that jives with his book. And he has this on page, it's equation 8.76 on page 451, but that's where it comes from. Y'all with me on this, guys? Now this, here's the way I always get this. I don't worry about this right here. I don't worry about the power density. If I know the E field, I got the power density. It's nice that it's so simple. It's all this stuff in front of them. There can be written as simply 15 I naught squared over pi R squared. And this would be watts per meter squared. With me? Now, I gotta tell you one thing about this. All right, that's the average power density. To get the normalized power density, one thing people do, and that's a mistake, is just say, well, just get rid of this stuff, it won't be that. The reason you can't do that is this is not a trig function that has a maximum value of 1. It can be much greater than 1. All right, so y'all hear me on this one? And because of that, what you have to do is get the maximum value of that. If you want the power density, what you're going to see is this. Normalized power density for an arbitrarily long antenna is really gonna be, that is f of theta, but it's over f maximum value of theta. You don't know what that is easily. Sometimes these are weird. It can have a very large maximum value. So that's the way you do it to get the normalized power. And once you have that, you can get the gain. And he mentions this on page 452. And he goes through it. Once you have the normalized power density, then you just integrate that times sine theta d theta d phi from 0 to pi, 0 to 2 pi, and divide that value into 4 pi. So you're gonna calculate the solid angle, all right? Everybody with me on this, guys? I'm trying to be clear. I'm trying to tell you what I would want to know if I was where you're at. Because most of the time, when I had the really good professors I had, what they did is they told me things when I was sitting where you were, that they wish they heard when they were sitting where you guys are at. In other words, they give you the sequence. Some profs that I've had, they don't do that. They go through the whole thing and, well, let him figure it out. And that's not good, in my opinion. You're paying for an education. You want to find out, really, you might say the secret stuff, the stuff that really matters, and that's the thing that really matters. Is get the E field, and then when you get, if you ever have to calculate gain, make sure you find the maximum value of that angular function, and then divide it into the actual angular function. Okay, now, I have more. Monday's off, so I won't see you until Wednesday. All right, let me finish this up with now the most common of the dipole antennas. It's called a half-wave dipole. We'll finish it there, and I'll show you. It's not going to be bad. Now that we went through this, just to give you an idea of how you get the E field from an arbitrarily long antenna. Now we talk about the most common antenna when it comes to dipoles. And some people would say it's the short. In my opinion, it's the half-wave. So for a half-wave dipole, this is going to be the lambda over 2 equals L dipole, or the half-wave dipole. All right, for a half-wave dipole, the length is L, the length is just L equal lambda over 2. It's a half-wave length long, right? The actual current distribution on this thing will look like this. If you actually plotted I of Z, it would look like this. It goes to 0 at the ends, has a peak value at the center. Now, I'll just show you what it comes down to the E field for that, and this is nice. This is the E field for the lambda over 2 dipole. Is just J60 over R times I naught times e to the minus j beta r, and then here's the nice thing. I want to make sure I got everybody's attention. All right, watch this. Half-wave dipole, right? This is for any, I mean, this is basically the E field for any length dipole, where this is f of theta, right? All right, for a half-wave dipole, when you look at this, beta L over 2. Well, beta is 2 pi over lambda, right? Then I have a 1/2, and then L is lambda over 2, isn't it, guys? Right. It's a half-wave long, so it's lambda over 2. Now look, what happens there? First thing you notice is the pi's, or I mean the lambdas cancel, right? Now I've got 2 by 2 goes away. So this is pi over 2, isn't it? When it's exactly a half wavelength, that's pi over 2 is beta L over 2. Do you all agree with me? What happens to this term? The cosine of pi over 2 is what?
0.
Cosine of 90 degrees is 0. It goes away, finally. So then I can say that this is equal to, here's my new angular function, cosine, right, of pi over 2, because that's beta L over 2, see that? Times cosine of theta over the sine of theta in the a theta direction. Now that's, maybe you're looking at this and you're not seeing why this is such a great thing. But this one is, this actual function right here is just about a sine. Not quite. It looks just like a sine of theta, almost exactly. So when you go ahead, and I'm not gonna, we don't have to do this, but the normalized value of this, the peak value of this function is 1. So the normalized value is that function, y'all follow me? So when I go ahead and get the directivity max, D max, that'd be 4 pi over, and it'd be a double integral from 0 to 2 pi, 0 to pi, that, which is the cosine of pi over 2 times cosine of theta, over the sine of theta, and then you have to multiply that by sine of theta, d theta d phi. Now, I'm just writing this down. You don't have to write all this down. Just appreciate what I'm showing. I just took it, the normalized power density, this has to be squared, my bad. This has to be squared for normalized power density. The E field, when I get the power density, I take the E field, I square it. I'm gonna have this angular function squared, right? Didn't I put that down? I did. So this goes away, and the normalized power density will just be this squared value of that, which is this, times sine theta d theta. That integration is another one that just doesn't jump off the page. Normally you do this, the sine theta squared, one of those cancels and you have a sine theta, and then you have this right there, squared. And at this point, you have to use Euler's to break this out. And then, I think it's UD, well, I haven't done this long. I think it's going to turn up into an integration by parts, but it's a bit of a mess, right? It's not something that's, at least that I see right up the top. When you, after you do the whole 9 yards on this, you get a D max, write this down, of 1.64 for a half-wave diamond. That's D max for a half-wave. L equals lambda over 2 dipole. And not only that, but the other thing you get is the D field, or the directivity as a function of theta equals D max, which is 1.64, and then it's times the cosine of pi over 2 times cosine of theta over the sine of theta squared. With me, that's the normalized power density, and that is the directivity. So if you got the directivity, and I knew the radiated power, then I could find the power density at any range. Here's one last thing about this. Now, with half-wave dipole antennas, I'm going to write this part down. When you have dipole antennas that are exact, and write this down, exact, L equals lambda over 2. All right, so they're exactly that. Then you get the antenna impedance. So this is what the antenna would look like if you plug it into a voltage source. All right, it's exactly halfway. You're going to have 73.2 ohms of real or radiation resistance plus J 42.5 ohms. Now circle this and call this thing R rad of a halfway dipole. That's the radiation resistance. So when we talk about a problem with a half-wave dipole, I want you to hear me. I'll let you catch up. This is important. Norm, can you shut that door, by the way? Normally you do this. You're going to have some voltage source here, some VS. Then you're going to have this thing connected to your half-wave dipole. Okay. So let's just say this Vs is the magnitude of the actual voltage. It's at some frequency. The steps you would take is first you need to find the current I, right there. And I would be equal to Vs divided by all the impedance, which is going to be Z antenna. Now Z antenna has a real and an imaginary part. You all follow me on that? Now you're going to get a value of current. You only care about the magnitude of current. But the power radiated, therefore, P rad, is going to be equal to 1/2 times the radiation resistance, which is 73.2, times that I squared. I squared is Vs over Z antenna squared, but you take the magnitude of this and square it. That's the total power radiated, right? Now, if you wanted the power density and you had the total power radiated, say we have total power radiated, how do you get the power density at any given R and theta? Huh?
1/2 times the magnitude of the E field.
Well, not quite. Don't we really, I mean, we don't, forget the E field for now. The way I always get it is what? Total power radiated. If we have that over 4 pi R squared, right? That's the isotropic power density, right? What do I multiply that by? Directivity or gain, right? The directivity is 1.64 times, and then would be that angular function, which is cosine pi over 2 times cosine of theta over sine of theta squared. And that would be the average power density. Anyway, I'm just telling you this. When you're solving these problems, you gotta get the current first. That means you have to divide the voltage by Z antenna, which has a real and imaginary part. Then once you have that, then you get the total power radiated, right there. And then if you have the total power radiated, then you get the average power density. And if I had the average power density, how would I get the E field? Now, go ahead. Am I talking too fast? If you have the power density, which is watts per meter squared, and I want the E field in the far field, what do? Equated to 1/2 E squared over eta, right? Then you could get the E field, right? All right, I'll give you I just had to get through that mile mark. You'll see a lot of this stuff comes together and makes a lot of sense. It's not so mysterious as this equation coming out. Here it is. How about we do it this way? First row fill up, second row empty. Third row fill up, this row empty. This row fill up, this row. I'll tell you what, make this row fill up. All right. Leave these two blank. Everybody, you guys move over. All right.